Okay, so hello everyone. So I'm Julien Dallot. I'm a PhD student at TU Berlin, and I will be presenting a novel approach to deal with predictions in with online randomized algorithms, which is called Infused Advice. Yeah, so I will be basically presenting you what this is and showing you two cool applications of this framework in in online caching and online set cover. So when it comes to framework with untrusted predictions, I just made a quick list of the most popular frameworks that are going on right now. So the first one is, I think, by far the most popular, the one with robustness and consistency. So you're trying to say stuff in two different situations whenever the oracle is true, is right, and whenever the oracle is anything, including adversarial or random or whatever. There is also some other frameworks for this. So there are the expert frameworks where you have n experts, each telling you his vision of what's happening, and then you have to decide to come up with processes to take decisions with this. Also, other frameworks when it comes to counting the number of advice bits that you need in order to solve a problem. And across of that, infused advice is a new model. So it was presented in 2023 by Yuval Emek, Yuval Gil, Maciej Patsut, and Stephen Schmidt. And I'm going to just tell you right now what this is. So infused advice can be used exclusively for online randomized algorithms. So nothing deterministic here. And so the basic idea of infused advice is to give predictions through the random seed, basically. So in most of the frameworks, you have a specific tape, specific place in the input of the algorithm to get the prediction. Here, you just get your random bits and the prediction through the same thing, your random tape. So for example, in Python, you can set the random seed really easily with a random module, just set random seed equal 42, for example. So in this setting, the infused advice model would be basically choosing a subset of random seeds such that your algorithm is going to be performing better than as if the random seed was just perfectly random as usual. So this model has many important properties that I will go back later, especially in the conclusion and when we go through the applications. There is some elegancy first, because at no point the algorithm has knowledge that he is actually influenced. Like, as far as he knows, the algorithm is just lucky, right? Because he just turns out to take the right decisions thinking it's random, but actually the random seed was written by an oracle from the very start. It's also more, let's say, handy for other things that we would like to do in normal algorithm analysis, such as lower bounds. Yeah, so we will see this in further details. So with infused advice, we are interested in long-running problems. So basically request answer games, such as caching. So we play something, then the adversary plays something, etc. And this goes on for a long time. So in particularly, we won't see the random seed as just one number, but as a string of bits. Yeah. And so there's going to be certain bits dedicated to certain actions. So basically, as the algorithm is running the instance, it is going to use more and more of its bits. In this model, in the initial model, the oracle is assumed to be trustworthy, but unreliable. So there are variants possible. I'm working on this right now, and I think this is a promising one, but this is as it was presented in its first release in 2023. And so, yeah, you assume that whenever the oracle is changing the random bits, it is for the better. So the oracle knows everything and just wants the algorithm to perform well, but it is unreliable. And in particular, it won't be changing all the random bits of the random seed, only a subset of them. So what subset? This subset is determined in the original model by an infusion parameter called alpha, which is a probability between 0 and 1. And this probability is basically telling you, well, what is the probability that the oracle is going to turn a random bit into a good one? So in more details, the oracle is just going to specify and to choose substrings of the random seed, and he's going to turn them into better bits. So knowing what the history of the algorithm is, what happened before, etc. He knows the code of the algorithm, he knows what's going to happen, and he just writes the right bits so that the algorithm makes the best action possible. Last thing about the model, we will assume that, yeah, the substrings modified by the oracle are those which contain the random bits that are dedicated to decide one action of the algorithm. So in a request answer game, we're basically going to assume that, well, each time the algorithm needs to do an action, for example, evict a page in caching or something like that, this is going to be a perfect action with probability alpha and a random one with probability 1 minus alpha. Yeah, and kind of a technical detail, because I think this is kind of a good assumption to have. We assume that all the algorithms we're dealing with here are randomness oblivious. This assumption is needed in order to avoid technical difficulties, but basically we assume randomness oblivious means that we assume the algorithm is going to use each random bit only once. So in particular, it's not going to take his decision based on random bits that were used before. He is always using fresh random bits, right? Okay, so just a quick summary of the situation. So the algorithm is reading transparently his prediction through the tape. And whenever he needs to do an action, the random bits that he's going to read in order to perform this action are going to be rewritten by the oracle with probability alpha, so the infusion parameter. Okay, so now we're going to see two application examples that are also in the original paper. So online caching and online set cover. Okay, so I'm going to do a quick recap of what the online caching problem is. So in caching, you have a cache, which is a set, right? I mean, it's exactly like a cache memory in computers. And the cache has size k. And you have items requested with time in an online fashion, so you have no idea what the future is when it comes to this sequence. And you have the following obligation: whenever an item is requested, you must have that item into your cache in order to serve that item. And if you don't have that item right now, you must fetch it. And fetching an item costs you time or whatever, and it costs you 1. All right. So of course the cache has limited size. So at some point you will have a full cache, and whenever you need to fetch something, you also need to evict something. And this is where the caching algorithm comes into place. A caching algorithm just specifies an eviction strategy, what to evict, because what to fetch is just forced. Okay, so online caching is historically the first studied problem when it comes to the consistency robustness trade-off by Chris and Vasilvitsky. So they studied the online caching in its randomized variant, and what they did is they modified a very well-known algorithm called random mark that was introduced first in 1991 by Fiat et al. And they proved that caching reacts very well in the in the consistency robustness setting. So in particular, when the oracle is good, you are constant competitive, and you are low K robust when the oracle is arbitrarily bad. Low K is the best possible, even when there is no advice. So this is simply the best possible, up to a constant factor. So with Infused Advice, we also changed the random mark algorithm. So I'm going to introduce quickly what the random mark is doing. So as I told you, caching algorithms are just specifying what item to evict into your cache. So this is the only thing we need to specify here. So the random mark is holding a dictionary for each item in its cache, but basically holding a Boolean value, 0 or 1, marked or unmarked. And whenever he needs to evict an item, he's going to do the following thing. He's going to take the subsets of all unmarked items from his cache, choose one uniformly at random, and evict it. Okay. And whenever everybody is marked, he unmarks everybody. Yeah, so the logic is pretty simple. We don't need to go into details here. We just need one property of the unmark algorithm for the next slide. So now I'm going to give you some insights of why is the online caching problem reacting so well when it comes to predictions. So yeah, so we assume that we have an instance of caching. So K is the size of the cache, sigma is a request sequence of items. And what we're going to do first is we're going to divide the request sequence into phases. So P1, P2, P3. So a phase is defined as you want exactly K different items to be requested in there. So, I mean, you can just start from somewhere. You see first item, you say, well, this is one first different item. Then you go on until you see a second different one, etc. And you go on until you have K of them. And then this is the end of the phase. We are dealing with such phases because it's pretty obvious to remark that any algorithm is forced to pay one, at least one, in such a phase. Because you have sorry, no, not K distinct item, K plus one. Because you have K plus one distinct items that are requested, and however clever an algorithm is, he can just store K items in his cache at the very beginning. So whatever his initial cache, the initial cache he started the phase with, there is always going to be at least one item he doesn't have in his cache at the beginning, and he's going to be able to have to pay one for this. All right, and now the question is how well does RandomMac performs in a phase? So let's focus on some phase PI, and let's assume that we have 3 pages. Let's call them X, Y, and Z. that are not in the cache at the beginning, but will be requested during the phase. So typically here, we can prove within the constant factor that any algorithm must pay for both pages because they didn't have it in the cache previously, and it's going to be requested during the phase. So somehow they must fetch those pages into the cache at some point, and they're going to pay free. Now I'm going to take 3 other items in red here that are pages that are in the cache at the beginning, but won't be requested. And so here you can see drawing a really easy optimal algorithm, which is just, well, at the beginning of the phase, just evict the 3 red pages, fetch the 3 green pages, you paid 3, and now you're good to go and you can pay 0 for the whole phase. And this is how I represent this algorithm with those arrows here. So one arrow here from X to X prime means, well, I fetched X and evicted X prime, right? So I just swapped them, right? And This is up to a constant factor, an optimal algorithm, what I just drew here. But random mark doesn't know about the red items. Like he will find that those items are not requested during the phase later. But at the beginning, he cannot know that those items will be the ones that he needs to evict in the first place. And a typical execution of random mark, instead of this optimal one, will look like something like that. So basically, he will eventually evict the page that is not requested, but on the way, he's going to also evict some other pages that he should not have evicted. So those white pages are additional cost, basically. And this is true for each of the green pages. So in the paper from Likoris and Vasilevitsky, they call those chains here blame chains. And the length of those chains directly tell us what the competitive ratio is. So in the case of random mark, so without prediction, you can prove that a blame chain has length at most log k, in expectation, which proves you directly that your algorithm is log k competitive because you know that for each green page, for each chain, opt is paying 1. Okay. So now that we introduce those blame chains, let's see what the effect of a prediction is on those blame chains. So let's say that we just have one blame chain like this, running the random mark algorithm. And let's say that at some point during its execution, the random mark algorithm has a prediction, a good one. So for example, he could know, well, what page to evict, let's say, at the middle. Let's say he gets it at x3. Well, you can convince yourself that whenever he gets the right prediction, he just knows what to evict. He can evict it right away. And in fact, what he's doing is he is breaking the chain loose. So he just took a big shortcut and said, well, I don't have to go through x4, which is another useless page that I should not have evict, additional cost. I just got one good advice, and that's all I need to cut the chain and get the don't pay anything more for this chain. So this is an interesting explanation why predictions are working so well with cachings, because one prediction is all you need to cut those chains. So now let's see how this is working with Infused Advice now. So with Infused Advice, again, each time you want to evict something, it's either going to be a random eviction with probability 1 minus alpha, or it's going to be the best possible with probability alpha. And well, looking at those chains, you can just see that I'm going to start by evicting the first one, then the second one, third one, etc. And by doing so, I'm just waiting until I have a right advice, an infused advice. And since this is all playing with a Bernoulli experiment, in expectation, I'm going to wait 1 over alpha until this happens. So this is the expected, an upper bound on the expected length of a chain, of a blame chain. So minimum of 1 over alpha, waiting until I have good advice, and hk, which is the harmonic sum, more or less equivalent to log k. Yeah, so that's as simple as that, basically. That's how you get a trade-off between 2hk as a competitive ratio, which is the best possible in online algorithm without prediction. And now you have also a 2 divided by alpha, a direct link with the infusion parameter. So this is the first result of the paper. And I'm going to introduce the other one, which is about online set cover. So let's start with set cover. So set cover, you have a set of nodes. Here, let's say I have 4 of them. And you have a set of sets, basically, subsets. And what you want is to cover all the nodes with as small a number of sets as possible. So here, for example, it's not possible to cover E3, so let's not care about it. And here, for example, an optimal solution would be 2, right? So we care about set cover because it admits a really elegant solution in online algorithm. Sorry, so in the online version, the edges are revealed in an online manner, right? So you don't have the full solution. You just have the nodes that are revealed one by one. And whenever a node is revealed, you must decide, well, should I add it to this? How should I cover it? And once I decide that I add this set, it is irrevocable and I cannot change it. Okay, so we care about online set cover because it admits a really elegant solution in the online primal dual framework. So primal dual framework in online algorithms is a technique where you basically reformulate your problem as an LP, a linear program, and you're going to do back and forth with the dual of that program in order to get some more inequalities to get to your result. And in online set cover, this works particularly great. So there's a seminal paper about this by Alan et al. In 2009. And they obtain a log n times log d competitive ratio. So n is the number of nodes, and d, is the highest number of sets a node is part of. It turns out that the primal dual methods can also be augmented with predictions in a relatively nice way. So this is done by Mas et al. In 2020. So here they describe some general tools and techniques to augment it with the popular consistency robustness trade-off. So in particular, they could get in an elegant manner optimal bounds on ski-rental in the randomized version of ski-rental. So they could get that because ski-rental is actually a particular case of set cover. Like you can see day 1 as just one set, day 2 as one set containing the 2 first days, etc. And then depending on the number of days that are revealed, you want to, finding the least number of sets is equivalent to actually solving ski-rental. So this is one of the applications it has. Okay, so this is the linear program associated with the online set, the set cover problem. So I indexes are for sets here, and xi is 1 if you chose to select the set to add it to your solution, 0 if not. And this is pretty straightforward. So you just want to minimize the number of sets that you select. And for each node, you want at least one set to cover it, right? So now I'm going to describe you the simplest method to use the LP formulation in order to derive a fractional online solution of online set cover. So in the online version, the constraints are added one by one. So this is the set of constraints, the matrix of constraints, who is revealed online. And whenever a new node comes in, you have a new constraint that pops, and you must right away find attributes, set your xi's such that the new constraint that just came is feasible. And the way to do it is the following update mechanism. So whenever you have a new element, sorry, this is E here, this is not I. whenever you have a new element E that arrives, you update xi as follows. So I'm not going to go in the details here. This is just to illustrate how we can actually use Infused Advice further based on this. So you multiply the previous variable for one of the sets that cover E by 2, and you add one of the FE, where FE is the number of sets that cover E. And you do that for each sets that cover E. So you can figure out that doing this actually makes the constraint feasible because you have FE such constraints and you add that parameter FE times. Okay, so let's say that an element E was just requested. I'm going to do a dry run of the algorithm. And let's say that we have a number of sets that cover E. So here we have 6 of them. So, and let's say that E is not covered yet, right? So you did not select each of those sets so far. So here we have FE equals 6, right? And we are just going to update xi, where I is each of the sets that cover E, 2xi plus 1/6, right? And it is possible to prove that such an algorithm gives you a log D competitive online algorithm. Now, we want an integral version of this. So how to do it? The technique is to see those variable xi as probabilities. So first, we're going to change perspective and see the evolution of the algorithm from a set point of view. So let's say this is a set I, and initially xi is 0, and we have requests to nodes, to E1, to E2, and whenever a requested node falls inside the set we're looking at, we are setting xi equals, we're just applying the rule, right? And we do that, etc., etc. So here is another rule application. Okay, so now we want to go from fractional to randomized. So how to do that? The way to do that is to, each time a node E is requested, where E is contained into I, we are going to select set I with the following probability. I'm going to show you why it works based on the fractional algorithm that we just saw. So here we are going to do 2 runs, one of the fractional solution and one of the randomized solution on the same example as previously. So initially, we have the variable xi for set I that is set to 0. Here, pi is set to 0, so pi is the probability to select the set at the given round. We request nodes, and whenever a requested node ends up inside the set, we are going to apply the rule. So here it turns out that it's the same on both sets. So here you're going to select the set with this probability. You keep going, etc., etc. And then here it comes. So you can find out that if you sum all the probabilities so far to take the set. So here you had 2 opportunities to select the set I. Here you had this opportunity with that probability. And now you have a new opportunity with this probability. If you sum all of the probabilities, you find the current fractional variable. And because of that, you can just apply a union bound and the linearity of expectation to just prove that, well, in expectation, I'm just going to have the same or better results than the fractional solution, because in the end, my probability is just exactly, is actually greater. The probability to take a set is actually greater than the fractional solution of my set cover instance. Okay. We still have one problem, which is that, okay, we have a solution with a certain guarantee on the objective value, but the solution may not be feasible, right? Because we just take sets at random, but it may very well happen that a node is requested and you just did not take any sets that cover it. So in order to do this, I'm going to go in the details, but you can just multiply the probability law that we saw by log n. And it turns out that by doing so, you have you end up with a solution which is log n times log d competitive with high probability. Okay, and now that we know all of this, let's see how we can solve this problem and make this solution better with infused advice. So, as usual, as previously, let E be a requested element that is not covered yet. So, the most intuitive idea would be to say, well, let's say that the oracle has in mind an optimal solution of the set, right? So the oracle knows the entire solution from beginning to the end, so he can just compute an optimal solution. And let's say that whenever he can write on the random tape, he can just tell the random algorithm, well, just take the right sets. So whenever E is requested, the algorithm is going to go through all the sets that cover that node, and the oracle can just influence the choices and say, oh, well, I'm going to make you take only the sets that are part of my optimal solution. The problem is it doesn't work here. Why doesn't it work? It's because we might not have a feasible solution in the end. That's because, well, we have a feasible solution with high probability. And this is with high probability only because we had balanced our randomness in the right way, right? But if we start to have every now and then a deterministic output because of the infused bits, then everything breaks and we might not end up with a feasible solution with high probability. So we are dealing with this by adding some more randomness into the infused bits. Yeah. Right. So let's say that the blue sets here are the ones that are part of the optimal solution of the oracle. He would like us to take those, but as I said, if he just forces us to take those only, we're going to end up with a deterministic solution, and then we're not going to be feasible with high probability. So the way to do it is to do a hybrid approach here. So whenever E is requested, and let's say that E is not covered yet, the algorithm is going to go through all of the sets here around, and for each is going to run a randomized experiment and decide based on the outcome, do I take it or not? So whenever the algorithm goes through one of the sets that is part of the optimal solution, so one of the blue set, the oracle is going to infuse a bit inside its random tape saying, well, take it. I force you to take it. And for the rest, whenever he goes into a black set like this, the infused advice, the oracle is actually going to simulate what the algorithm would have done. And he's going to say, well, take it with the same probability that we saw before. or not take it, right? So we're basically delegating the random choice to the oracle in that case. And yeah, it works. So what we get in the end is the log n factor, and we get a drastic improvement in terms of the second multiplicative term, the log d. So we have a mean of 1 over alpha, where 1 over alpha is, for the same reason as before, the expected length of a geometric law of parameter alpha, and log d. Okay, so to conclude, so the Infused Advice framework is coming with some opinionated assumptions. So we assume that, we assume that the algorithm is randomness oblivious, as I said. So there must be some assumptions on what algorithm we're dealing with. That's not, I never saw an algorithm that is not randomness oblivious. So maybe you can tell me if you know one algorithm that uses one random bit multiple times. Also, we assume that the oracle is going to write in the random seeds following a Bernoulli process experiment, right? So this is just made for simplicity, right? In order to quickly be able to analyze algorithms that are otherwise complex to analyze in other prediction frameworks. But when we are past those opinionated choices, we discover a really simple yet powerful framework that still make it possible to improve on known bounds and still make it possible to have trade-offs, right? Because of this alpha parameter. Yeah, so the infused advice is really generic. It applies to any randomized algorithm as long as it's randomness oblivious for simplicity of the analysis. Yeah, like in other trade-offs, over frameworks like consistency, robustness, we can talk about inherent trade-offs by tinkering with the value of the infusion parameter alpha. And in my eyes, it also offers some more extra. So we do not need to wonder about what are the predictions. We do not need to wonder about an error function. Everything is just in the form of random bits. So this is as simple as a prediction can get. The framework is cleanly defined. And so in particular, it is possible to derive general lower bounds here. So this is a really attractive point in my opinion. Like the simplicity and the cleanness of the framework make it possible to do to actually solve problems, right? To have tight bounds. Like for some problems, it is possible with the consistency trade-off framework. It is possible to talk about lower bounds, but it's quickly become really intractable as the problem get bigger. So people are, for example, proving lower bounds for specific error functions, so specific ways to account for errors. Here, it's really easier to do it because the framework is simple and straightforward, and there is no error function that you need to think of. And finally, it's very extensive, so you can. So in the original version, for example, you assume that the oracle is always trustworthy, but unreliable. It's pretty straightforward to just change it and say that sometimes with some other probability, the oracle might be adversarial, for example. And it's still possible to analyze it in a clean manner. Yeah, we can also, for example, change the way that to decide when the algorithm, when the random bits are going to be infused or when they are going to be actually random. This is all a matter of modeling. But yeah, overall, this is a simple yet powerful framework. And yeah, I hope it will gain in attractiveness because yeah, I think it enables to have quick results, usually easier than with other frameworks. Thanks a lot for your attention. I'm looking forward for your questions if you have any.
Questions? Yeah, the microphone died.
Yes.
Yes, the canonical guys of this, I think, is about learnability of these predictions, like of this infused, where does this infused advice comes from for this?
When does the infused advice come in is actually
I guess like how do we get this advice? Like,
so this is complete black box. We have no idea. Yeah, like we make minimal assumptions here, so it may very well be machine learning or whatever. Yeah. So here the machine learning needs to know about the actual code of the algorithm in order to put relevant random bits, right? Yeah.
I'm wondering, do you have any like empirical evaluations using like your algorithm, for example, in the hashing system, and also like online sensor placement? This is.
So you're asking whether it's applicable in Universal? Yes, it is. I mean, it's really generic, so you can just apply to any randomized algorithm, right? So as long as it must not be deterministic. For deterministic, other frameworks are perfect. But for randomization, yeah, you can just use it. Absolutely.
Unless you were still.
Yeah, I was just going to say that I think it make more sense to use it for long-running problems. So for example, for ski-rental, this is a one-off. You can still use it, of course, but it may be less relevant because in the end, the maths may be really trivial. Like you just say, well, I just make one choice. If it was infused, then I get the best of it. If it was not, then I don't. Maybe trivial in that case, but you can get really interesting results when you have long-running instances, like in the caching or covering problems. So I think it's more suited for that kind of problem. Yes.
Yeah, I have sort of one question and then one. Yeah, it's also a question. So it's two questions. The first one is, I think, kind of related to what Fedora's has, which is that have you thought about how easy it is to analyze an algorithm that has infused advice if the infused advice itself is not exactly correct, right? So like you flip the bits, but like one of them's off,
Yep.
right? Like
Yeah,
easy to analyze, or does that break?
It's possible. So I'm actually doing it right now.
Okay.
Like so as a I mean, my PhD thesis is about finding. I mean, what I would like to do is finding generic techniques to find lower bounds for prediction. So I would like to. We have a Pareto front, and I would like to be able to find techniques to say, well, this is the best we can do. And I've been looking for such a thing for 1 year now, for the consistency robustness framework. I have some stuff, but it's really complicated. Like even in a deterministic setting, I mean, what I would like to do is do something that is error function agnostic, right? So I would like to say, well, if you're doing that good in the consistency case, then you must be doing that bad. So in particular, if you're doing that bad, then there exists an input sequence and there exists a prediction such that you're doing particularly bad. And regardless of how you measure the error, etc. And in order to do that, I mean, it's really complicated. For ski-rental, it's possible. For small problems, it's possible. But when you get to complicated problem or randomness, I don't know how to do it right now. But with this framework, it's possible. So you can actually talk about oracles that tell you nasty things. So you can add an alpha prime here, for example, let's say, well, maybe sometimes the advice is not so good, and you can tinker those values to reflect whatever your real model is, and it works. You can actually do that in concrete problems.
My one final was just kind of a question, kind of a comment. I think it's a question because I don't know how it would affect the analysis, but I know of one randomized algorithm that kind of reuses random bits, which is the it's not really strictly true, but if you know the optimal randomized algorithm for metrical task systems, arbitrary metrics, so shown by Hubeck co-authors in 2019, the problem with metrical task systems is that it's stateful, right? You have a state, you have some location in the metric that you're at. And so the way that they make this algorithm randomized is you have some probability distribution over states.
Yeah.
And then you couple your decisions, your randomized decisions over time using the Washer state one or your distance between these probability distributions.
Okay.
And so it's sort of like your switching cost at future times, if that makes sense, depends on what your random
Decisions.
decision was at previous.
You're thinking about random oblivious here.
Yeah.
So this is, I mean, for an algorithm not to be randomness oblivious, you need to be in a very specific case, I think, because, and obviously an algorithm needs to take its random choices depending on what state he is right now, right? Otherwise, he would need, I mean, might be forced to do illegal moves, that kind of thing. So yeah, it matters because it just makes everything simple, because then everything is IID. Like all the actions of your algorithm, I mean, you just don't care. You don't directly care about what the random bits were, but you care about the consequences of those random bits. So the consequences is then the algorithm played this, and then now I'm here and I need to take it into account. So this is taken into account, but what the random bits specifically were doesn't directly impact.
Great, let's see if we can go on. All right, so I won't hold people up. I know it's like the end of the day, but that pretty much closes out the workshop. Thank you so much for coming and sticking around for the whole day. Yeah, I think that's it. It was a wonderful iteration. Looking forward to seeing you next year.